the school and the organizers for this opportunity. And thank you all for coming. I hope you enjoyed this. So, so I'm going to talk also on the right-hand theory of finite dimensional algebras. And so we're going to talk about representation theory of finite dimensional algebras, and we're going to take a quiver point of view on the subject, which hopefully a few of you don't know. I think I've seen already a few of the participants who already know these things. But okay, so I'm actually not going to talk yet of what's on the right-hand theory in this lecture. First, I need to give a motivation and an introduction for this. And basically the point is to tell you why it's good to talk about quivers in this area. So I'm going to start with saying what a quiver is, and then we can associate an algebra called path algebra to a quiver. We're going to define this, but in order to be able to extend this language to study any finite dimensional algebra, we need to extend these algebras by looking at quotients, and we'll call this bound path algebras. So it's certain ideals that we need to add to this. Okay, so we can associate a bound path algebra from a quiver, and then we'll see a result that says that from the representation theoretic point of view, it is enough to consider all this kind of algebras. So from what we want, we can just consider path quivers and bound path algebras, and this will suffice. Then, the central point of, I suppose, of representation theory is to study modules and morphisms over an algebra. And so what we're going to introduce later is how to visualize those in terms of the quivers and the admissible ideal. So we're going to call this bound representations. I'm going to define this. This will produce a new category, which is called the category of representations of bounded by I. And then the central point is that the module category over any finite dimensional algebra is equivalent to the module category of a bound path algebra, and that can be seen as this new category of representations. So we can just use basically linear algebra in the quiver to look at all the modules. And then I hopefully, if I have time, I finish with the natural question, which is to think of those algebras which have the simplest somehow module category, and that is in terms of having a finite number of modules. And I'll give a nice answer to this, which is a classical theorem in the area, which is called Gabriel's theorem. Okay, so first I'll say what a quiver is. So a quiver is basically just a directed graph. So it's got a set of vertices, which will be denoted by Q0. It's got a set of arrows denoted by Q1. And then these arrows, so the directed edges, they start at a point and they end at a point. So we'll find these maps from the set of arrows to the set of vertices. When S is the source of the arrow, T is the target of the arrow. So we have this. Well, why not just call it directed graph? I'm actually not sure. I think someone who invented this was quite clever and saw that the quiver actually is the name of this bag that archers use where they put their arrows. So it's like a collection of arrows. And so I think this is where the name came from. It's more fun, I suppose. Okay, so we'll only consider finite quivers. So we just want a finite number of vertices and a finite number of arrows. So examples. So we can have a simple example like this. We can have what is called loop. So this arrow here starts and ends at the same vertex, and there's only one vertex here. we can have multiple arrows, which is more than one arrow going from one vertex to the other. We can have that. We can have more complicated vertices, or quivers, I mean. You can have this, and then a loop here, another arrow there. I'm going to also just consider connected. So from two vertices, you can always connect it. It doesn't have to be an oriented path, but you could consider these two separately, but it's simpler to just consider connected quivers. Okay. Right, so in order to define a path algebra, I need to define a path, first of all. So what is a path? A path of length L, and here L is bigger or equal than 1. So this is just a sequence of arrows. So each of these alpha i's are in key 1. And it has to be oriented. So, and I'm going to read paths from left to right. So what does this mean? So the source of alpha I is the target of the previous arrow, alpha I minus 1. So this path will start at the source of alpha 1. This is also called the target of the source of P. And we'll carry on up to the target of the last arrow alpha L. And this is also the target of the path P. So these define paths of length bigger or equal than 1. But we also want to add some paths of length 0. And this will be associated to vertices of the quiver. So for each vertex, we will associate a constant path. These are also called lazy paths or stationary paths, if you see it in the literature, and we'll denote it by this, epsilon I. Okay. And so we could have that the source of alpha 1 is the target. So it starts and the path starts and ends at the same vertex. This is called an oriented cycle. And as we've seen in the previous example, if this path has length 1, then this is just a loop, right? Okay, and we say that a quiver is acyclic if it doesn't have any of these oriented cycles. Okay, so the example, I could go here. Copy. Paste. Right, I need to give names to these people. So alpha 1, alpha 2, alpha 3, alpha 4, alpha 6. Okay, so you could, alpha 1, alpha 3, for example, is a path of length 2. Then you could go alpha 1, alpha 4, alpha 5, 3 times, say, and stop there, or continue and put alpha 6. This will be a cycle. But you can't have alpha 4, alpha 2, say, this is not a path. And yeah, you get the gist. These are paths of the quiver. And so now I'm ready to define a path algebra. Okay, so for simplicity as well, I'm always considering the field to be algebraically closed field. And as I said before, Q is going to be a finite quiver. And so as the name indicates path algebra, we're going to look at paths on the quiver. So an algebra as an underlying vector space. And as an underlying vector space, this will be generated by all paths of Q. But then we have to define a multiplication. And so, well, we'll first define the multiplication on two paths. So if you have P and P prime, this is the intuitive thing you do with this. So you have two paths, you concatenate if you can. That means if a multiplication PP prime is the concatenation if the if the path P ends in where the path P prime starts. But this might not happen, so if that doesn't happen, then we just define the multiplication of those two paths to be 0. Okay, so this defines the multiplication of paths. And then we want the distributive law, but we can just extend this by distributivity. So any element of the algebra is of this form. Let's say this. So these lambdas are in Q. These are paths. It's a linear combination of paths. And then if you multiply well, this is just extended by multiply these scalars, and then you concatenate all these possible paths together. Okay, and this defines the algebra, path algebra. Okay, like examples. So let's look at this quiver. What is the path algebra? So as a vector space, this is generated by paths. Remember, there's paths of length 0. There's only one vertex, so there's only one constant path. This is 1, sorry. And then there's the arrow alpha. And then you can compose, because it's a oriented cycle, you can compose this. You just get multiples of alpha. And as you can see, this is infinite dimensional. But you can actually set up an isomorphism between this algebra and the algebra of polynomials on one indeterminate. So if you, you can associate the constant path to the identity here, and then alpha 2x and so on. And this defines an algebra isomorphism. Okay, so this is an example of an infinite dimensional. Let's look at a simpler example. And in any talk on representation theory of quivers, it's going to be rare that you don't find this example. There's always a type A3 example or type AN. Okay, so what's this? Path algebra, then, so we have 3 constant paths because there are 3 vertices. And then there are the arrows, alpha and beta, and then concatenations. There's only one concatenation possible, alpha beta. And this is all the paths of the algebra. And again, you can set up an isomorphism between this algebra and the algebra of matrices, upper triangle matrices. Nice. So what do? You assign the constant paths epsilon I to the matrix with K in the ith element of the diagonal and zeros elsewhere. So this will be epsilon 1, epsilon 2, epsilon 3. And then the other paths, you see where it starts and where it ends. And so, for example, you correspond to the matrix with K in row I if the path starts at I, and column J if the path starts at J. So here we would have paths from so this guy here. Yeah, you'd have paths starting at 1 and ending at 2. So this is alpha. This is 1 and starting at 1 and ending at 3. So the alpha beta. And here would be beta. Okay. Just one more example. A complicated example here. Well, as you can see, this is also going to be infinite dimensional. So you have what are the generators. So it's the constant paths. For each vertex. Then you have the arrows. Then you have, for example, alpha 2, alpha 3. Then you can compose alpha 1 with it, concatenate alpha 1 with itself, no matter how many times you want. You can do that and then add alpha 2 or alpha 2, alpha 3, or alpha 2, alpha 3, and then no matter how many alpha 4s you want. And you can do the same with alpha 4. Alpha 4, alpha 4 before alpha 3. Okay, so this is for any. Okay, so this is infinite dimensional. And so you can multiply these stationary paths, for example, epsilon 1, alpha 1. So you can concatenate this because alpha 1 is at vertex 1 and alpha 1 starts at 1. So this is okay, and this is actually alpha 1. But you can't do, for example, epsilon 2, alpha 2, because alpha 2 doesn't start at 1, so this will be 0. But alpha 2, epsilon 2 will be alpha 2 because alpha 2 ends at 2. Okay, so this is concatenations of paths. And you can guess from these examples the following properties. So the path algebra is associative. This is by definition. And the path algebra has an identity, which is given by the sum of all these constant paths. And for this you need the set of vertices to be finite. So you have a finite sum here. And because we're only considering finite quivers, then we always have an identity. And as you've seen as well, this path algebra is finite dimensional if and only if Q is finite, because we need a finite number of vertices, because this gives a stationary path, a finite number of arrows, because he is also part of the basis, and he can't have any oriented cycle, so it needs to be a cyclic. Okay. But we can still consider with oriented cycles and just be fine, infinite dimensional. So the next step is to extend these algebras to quotients. But for this, I need the definition of admissible ideal. Okay, so if you take a finite quiver, first we're going to define the arrow ideal, which we'll denote by RQ. This is a two-sided ideal of the path algebra, and this is just generated by all arrows in Q. Okay, so admissible ideal is what? Is also a two-sided ideal of the path algebra, for which there is an integer bigger or equal than 2m, such that we have this. I'll say briefly afterwards what does this mean. But yes, so I'm going to, usually when we talk about this I, we talk about relations. So what is this? So if you take the admissible ideal I, is generated by, let's say, some elements here. Then for any vertex x and y, you can consider epsilon x, sigma I epsilon y. And so this will be linear combinations of paths which start at x and end at y. So linear combinations of paths, and this will be bigger or equal than 2 because of this condition. And the start all these paths have the same start, which is x, and all these paths have the same target, which is y. So this is what is called a relation. This is also written here. Okay, so a linear combination of paths of length, each row of those of length bigger than 2, which start in the same vertex and end at the same vertex. And so, yeah, so for each sigma I, you can write this as a linear combination over all the vertices of this. So you can see that I can also be generated by, sorry. This epsilon I here. You can see that this is also generated by this. Which are relations. So we can say that any admissible ideal is generated by relations. This is all I'm saying here. Okay. Right. Right. And so if you have an admissible ideal in a path algebra, you can do the quotient, and this is what's called a bound path algebra. So why this condition? So, well, this RMQ is basically just the ideal generated by all paths of length bigger or equal than m for a certain integer m. This means that if you quotient out, so if this is contained in I, and if you quotient out, then any path from a certain length is 0. So this means that there's an upper bound for all the paths that are allowed, and so the bound path algebra is finite dimensional. Okay, and this condition basically means that the algebra, we want the algebra to be connected, meaning that it's not the direct product of two algebras. Basically, this is saying that we're not cutting arrows, and this can be proved to be the same as KQ over I is connected. Okay. So examples. So if you have this, well, you can consider the zero. And I saw someone, I heard someone say. So this is actually not admissible, this ideal, because you can just have beta m for any m, is not 0. So in fact, if Q is not a cyclic, then I equals 0 is not admissible. Well, for the same reason, for example, if we do alpha beta, this is also not admissible, because you can still have beta m. So we need, for example, something like this to be admissible. As long as it's not just beta. Sorry. Yeah. Okay. Just one more example. So here, for example, if you consider alpha gamma, and also this ideal generated by alpha gamma minus beta gamma. Again, notice that these are relations. So this alpha beta gamma minus beta gamma is a linear combination of paths starting at 1 and ending at 3. These are admissible. And actually, if you look at the bound path algebras, you can actually set up an isomorphism if you map the stationary paths to the stationary paths, and then alpha to alpha minus beta, gamma to gamma, beta to beta. These are actually isomorphic. So this admissible ideal is not unique in some sense. Okay, so this is the point why, I mean, you can say that this is not general enough. This is a nice class of algebras, but it might not be enough. But if you want to study finite dimensional algebras, and if you want to study the representation theory of it, the module category, then it is enough. Then this says that if you have a finite dimensional algebra, there is always a finite quiver and an admissible ideal on the path algebra of that quiver, such that the module category of A is equivalent to the module category of this path algebra, bound path algebra. This is also said, people also say that they are Morita equivalent, these algebras. So if you want to study module categories, then over finite dimensional algebras, then it's enough to consider quivers. And this is quite nice. But so as I said, we want to study modules. How do we actually see this in the quiver? So we just explain how to see an algebra from a quiver. Now we need to define something that will correspond to modules and morphisms. So this is what these representations are. So I'm going to consider finite quivers, as I said, connected for simplicity, and I is going to be an admissible ideal. So we can define a representation of Q. So first, and for now, ignore this I. And this is actually can be defined for any finite quiver. It doesn't have to be a cyclic. And what is this? So this is going to be a set of vector spaces associated to each vertex of the quiver. And then you have arrows. So it's natural to associate with linear maps between these vector spaces. So phi of alpha is going to be a linear map from mi to mj if the arrow goes from I to j. Good. So this defines a representation of quivers. And then if you want an admissible ideal imposed on Q, if you want the representation Q to be bound by I, which can also be said that is a representation of Qi, then you want to have something to do with these relations. So for this, I first need to define what this phi of rho is. So if you start with the path from alpha 1 to alpha L, we can evaluate the representation on this path. And this means this is just the composition of these linear maps. And then you can extend this by distributivity for any relation, right? So what we want is if rho is a relation, then if this linear combination of compositions of linear maps must be 0. Right, and basically everything that I want to talk about is going to be finite. So we want finite dimensional representations, we want finite dimensional modules. So I say that the representation is finite dimensional if each of these vertices, if each of these vector spaces are finite dimensional. Okay, so for example, let's say this quiver bound by this relation, alpha 2, alpha 3 minus, sorry. Minus alpha 4, alpha 5. Okay. So this is the same as going here. Right, so this representation. So associate the vector space K to vertex 1, K squared, K, 0. I'm going to say this will obviously be 0 because the target is 0. Well, because the target is 0, it doesn't matter actually which maps are here, because this composition is 0 and this composition is 0, so the difference is 0. So this is bound by I. But if you have, for example, K here, K, 0, K and K, and these linear maps here are just the identity, then as you can see, this is 0 minus 1 is not 0, so this is not bound by I. So this is a representation of Q, but it's not bound by I. Okay. Right, so next step. So I want to define a category from this. So I define objects. Now I'm going to define morphisms. So if you have two representations bound by I, or not bound by I, doesn't matter in this case. So if you have a morphism between them, it's going to be a collection of linear maps again. From Mi to Ni. And this will produce squares like this. And if you study category theory, then someone basically, if you see a square, you want it to commute. And what does this mean? So it means that going this way, so Fj after phi alpha is the same as going this way, psi alpha after Fi. Okay, so you want this to be 2 volt. And then you can have two representations being isomorphic if there is an isomorphism between them, meaning that each of these Fi's for each of vertex is bijective. So in particular, if they are finite dimension, you have to have the same dimension on at each vertex. Okay, so I'm actually considering this. I know it's not cyclic. Just consider this, not bound by anything. Then you can consider this representation of the quiver. And you can look at another representation like this. Okay, so what's a morphism between this from here, from the top to the bottom? Well, it consists just of one, because there's only one vertex, so it's just one linear map, F1. Let's see if this works. So basically what you have to do is this composed with this is the same as going here and then this, right? So you have to check that 3, 0, 1, 2 after 0, 1, 1, 1. This is, if you do the maths, is this, if I'm not mistaken. This is the same as, so this one after this first one, 2, 0, 0, 3. So this is a morphism of representations. And you can check that it is an isomorphism, because you can define another map going up such that the composition is the identity. Okay, so actually this is the reason why I wanted to do this example is actually quite nice to associate this representations of this quiver with something studied in linear algebra. So if you have, for example, two representations with the same dimension here, let's say matrix A here and here B, When are they isomorphic? Well, this is the same thing as saying that A and B are similar. So there is an invertible matrix P such that A equals P minus 1 BP, or PA equals BP. So this means that it's a morphism. Means that it's an isomorphism. Okay, cool. Oh, I forgot that the screen doesn't. Okay. So this defines a new category. So we have, for a category, we need objects and morphisms. And you actually, this is something easy to check, that if you have two morphisms of representations, you can compose it, and you can still see that the square commutes. So we can define compositions of morphisms. And so we're going to get a category of representations of finite dimensional representations of Q bound by I, and the morphisms like we define. And as I said in the beginning, this is quite nice because you can associate to this bound path algebra. You think of the modulo category, but it's the same as thinking of this category, where you just look at vector spaces associated to vertices and linear maps associated to arrows. Yes, I think I have a bit of time to do a sketch of a proof. So I don't know, probably quite a few of you have background on category theory, and this is ideal to know a bit of category theory for this, but I mean, it's not, you can survive with that. It's just to have an idea. So sketch of a proof. Okay, so what we're going to do is define a functor from one category to the other, and then define another functor the other way around, which is called the quasi-inverse, so that the composition gives somehow the identity morphism, a functor, sorry. Okay, so step one, I'm going to define a functor from mod, and I'm going to call KQ over I equals A, just for simplicity. So from mod A to rep QI. Okay, a functor, you need to find it on morphisms and objects. So on objects, so you start with a module, finite dimensional module. You're gonna have to define M must be a representation, so it's something of this form. So what's MI? So MI is M, and then you multiply this, because this is a module over A, it's path algebra. You can multiply on the right. I'll say mod A is the right modules. Multiply on the right by this element of the algebra. So MI is quite natural, right? You associate the stationary path associated to this I. I also denote this by EI, like this. Okay, so I define these MIs. What are the linear maps? So this goes from M S alpha to M target of alpha. So something in MS alpha is of this form, so M E S alpha. And this map just multiplies M by alpha bar. So it just multiplies this by alpha bar. Alpha bar is what? M alpha plus I. And because alpha ends at the target of alpha, this belongs to MT of alpha. So, but as you've seen, we've defined a representation of Q, but we didn't check if it's bound by I. We need to check this. So we need to check that FM is bound by I. So what does this mean? So you have a relation will be a relation, so it's a sum over some paths. Let's say they start at I and then at j, so this wiggly arrow is just a path. Alpha p and k, p. So suppose this is a relation in I. We need to check that the evaluation of fm on this relation, so this is going to be 0. So this starts at m of mi, because I is the start of p, of the row. So this is, now, so take an element of mi. So this is this linear combination of the evaluation on this path. What's this? So by definition of these linear maps, so on each arrow you just add the arrow, and so at the end you're going to get p. So it's m p plus I. Okay, but now we can play with the properties of the module. So you can put m outside, and you get this. But p, so this is a row. This is a relation in I. So this is going to be this is 0 because it's a relation. So this is 0. So this means that the evaluation on the relation is 0. So this fm is bound by I. So we check that. So all right. So we just proved that this defines representation, and then on morphisms. So you have a map from M to N in mod A. Let's say Fm equals Mi phi alpha, and Fn equals Ni psi alpha. So I need to find a morphism of representations. And so this is quite natural. So Fi goes from Mi, so an element here. We just define to be f of m. This is in n, and then it needs to be in ni, so we just multiply by ei. Right, okay. So you need to check that in order to be a morphism of representations, you need to check the commutativity. Of j and ej psi alpha. So you need to check this. Well, it's easy with the definitions which is given. I don't have much time now, so to wrap this up. So you need to check this. This defines a morphism of representations, and then it's easy to see that this actually defines a functor. So the f of an identity morphism gives the identity morphism, and it behaves well with the composition of morphisms. Then the step 2 is to define a functor going the other direction. So from representations of Qi to mod A. So again on objects. So you start with a representation here. You need to find module from this. So how do we do this? So let's call this M. So it has an underlying K vector space. So as a K vector space, you just add all these MI's. Okay. And then you need to define a right action of A, of this bound path algebra A. So right A action. And it's actually, we want to have distributivity, so it's enough to check on paths, enough to define on paths. So we have paths of two types, right? One of length 0, So take M in M. So this is a tuple, n tuple if the number of vertices is n. And if the path is stationary, then we just define MP to be M epsilon I, that's Mi, okay, the ith element. And if P has length bigger or equal than 1, then MP, so it's an n tuple, so the kth coordinate of this is, well, if k is not the target of P, then it's 0. But if k equals the target of P, you can apply for phi of alpha, so sorry, P. So this starts at M, start of P, so you can apply it to this element. And this ends at MT of P, so it belongs there. Okay, so this defines it. And again, you need to check that this is well defined. So what does that mean? That if we have a relation in I, then M, you extend this by distributivity, and M multiplied by that is 0. So need to check. And how long do I have? 47 minutes. Okay, I need to wrap this up. So the next step on this proof is to check that these are quasi-inverse of each other. But all you need is these definitions, and then you can check this. Right, okay. Yes, you still need some pages to check, but it's okay. Right, okay, so now I wanted to briefly state Gabriel's theorem, which is a big theorem, but it's quite important. So for that, I needed to find indecomposables. So from two representations, you can define a new representation, which is the direct sum. And this is you just add each of these vector spaces and each vertex, and then the linear map defined by this. That's fine. And so then you say that representation is incomposable if it's non-zero. So if it's not 0 on every vertex and all the arrows are 0 maps. And if M is isomorphic to a direct sum, then one of these is 0. It's the classical version of indecomposable. Maybe I'll give an example next time. So the representation, this category is equivalent to modulo category. We know this is a Abelian category, and it's Krull-Schmidt. What does this mean? So it means that any representation can be written as a direct sum of indecomposable representations. So it's enough from representation point of view, you want to classify all the representations, it's enough to look at the indecomposable ones. So it is natural to ask then, what, when does a quiver, or when does an algebra have the simplest representation? For example, when do they have a finite number of indecomposable representations? Of course, up to isomorphism. And such an algebra, or path algebra, is called representation finite, if there is a finite number of indecomposables. There is a nice answer to this question for this special class of algebras called hereditary. So this is basically those where I equals 0. So it's an algebra which is a path algebra of a finite connected acyclic quiver. Okay, we want to be finite dimensional. And so the result says this. It's quite elegant, and it says that an hereditary path algebra is a representation finite if and only if the underlying graph is of type A, D, or E. Yes, this is quite nice because this ADE classification appears in many areas. For example, in Lie algebras, in cluster algebras, as we're probably going to see in the second week. You might see this, and here as well. So it's quite a nice theorem. Okay, what happens outside? And I'm going to finish here. So any algebra that is not representation finite is representation infinite. And there's a theorem that says that there's this trichotomy. So it's either finite or tame or wild. So tame means that in some aspect you can still parameterize. You can still have hope to classify the incomposables. There's a way to parameterize these objects. And wild type, as the name indicates, there's just no hope whatsoever. So you can actually find, this is not the proper definition, but you can find the representation theory of any finite dimensional algebra inside the representation theory of a wild algebra. And just to see, this is quite nice. If you have this quiver, this is of type A, 2. So this is finite. If you have 2 arrows, this is no longer finite, but it's tame. We can still study their representations. But if you have 3 arrows, then it's just no hope. This is wild. Okay, in the next lecture, I'm actually going to talk about also on the Autumn theory, and basically I'm going to tell you how to look at the representation theory of some algebras, especially these hereditary ones, finite type, in terms of a quiver called the Autumn quiver. I'll stop here. Thank you for listening.